All right. So there we go. All right. Where was I? Okay. So chapter 22 is the chapter on amines. So we finished the long four chapters. So chapters 18, 19, 20, and 21. Those are the four biggest chapters that you cover in chemistry 31, 11. So we're back to kind of the regular length chapters, I guess you could call these. So chapter 22, introduction to amines. I know you all know what an amine is by now, right? If I showed you way back in chapter 2 of organic chemistry, or maybe chapter 1, I don't remember, we talked about functional groups, but you'd say if you see something like this, you would all describe that as an amine. But amines are actually derivatives of ammonia, and you guys all know ammonia from way back in your Gen Chem days, right? You learned how to name ammonia. And we can designate amines as being primary, secondary, or tertiary. And so this amine that I wrote over here in the circle, this is actually more correctly described as a primary amine. If you have two R groups on your nitrogen, that's called a secondary amine. And if you have three R groups on your nitrogen, that's called a tertiary amine. And so what this does is it actually makes the nomenclature of amines a little more complex. Primary amines are kind of named the same way you name an alcohol. But when it comes to secondary and tertiary amines, we have to come up with another strategy for naming those. All right, so everybody knows what ammonia is. It's NH3. Ammonia in its pure form is actually a gas, okay? So when they put ammonia in a cleaner like Windex, they actually bubble the ammonia in water and they make the cleaning solution from that. But if you have an amine found in nature, so there are lots of naturally occurring compounds that have amines in them. We call those alkaloids. So alkaloid is a word that chemists should know. If you hear of alkaloids, we're just talking about any kind of natural compound that has nitrogen in it. And if you take a look at this compound here over on the far left, this is morphine, and you've probably all heard of morphine before. Maybe somebody has even had morphine given to them before. I did. One time I was in an accident and I got some morphine and it was pretty cool. I can tell you that much. It felt pretty good. And, for all those people out there that say, oh, don't consume this compound, I'm not talking about morphine, but if they say, well, this compound is very close to plastic or this is close to a poison or something like that. Well, you guys know what an acetyl group is, right? You all know things like acetyl coenzyme A. So an acetyl group is just this, right? It's just that. Okay, that's an acetyl group. If you put an acetyl group on here, okay, and if you put an acetyl group on this oxygen, which is very easy to do, right? All you'd have to do is take the compound and treat it with acetyl chloride to put the. In that case, you'd end up with heroin. Okay, so heroin, and heroin you might know it by the street name like Skag or Smack, but anyhow, so heroin is very closely related to morphine. So you see how it doesn't take much of a change to alter the potency of a compound. Anyhow, also cocaine. You guys have all heard of cocaine before. You've all seen enough TV and movies to know what cocaine is. Well, this structure here is actually the free base of cocaine. Cocaine is actually the hydrochloride salt. So cocaine actually has this nitrogen protonated to make a cation, and then it's a hydrochloride salt. So that way it's water soluble, so that when it's snorted, it's absorbed through the nasal passages, very quickly. But if you take it and you freebase it, so meaning you take cocaine and you treat it with something like sodium bicarbonate, then it becomes the freebase, and that's how they make crack cocaine. So crack is made by taking cocaine, which is a hydrochloride salt, and then treating it with a base like sodium bicarbonate or something like that. Anyhow, the next one here is nicotine. Okay, yeah. So nicotine is the addictive compound that's found in tobacco smoke, and you can see that it's got two nitrogens in it. So what a cocaine, morphine, and nicotine and crack and heroin, what do they all have in common? They're all alkaloids. They're naturally occurring amines. And you see that, morphine comes from the poppy plant, cocaine comes from the coca plant, and nicotine is found in tobacco. So natural. So when somebody says this is natural, you can say so is cocaine. Anyhow, so some naturally occurring amines are vital to neurochemistry. And I could go on a long diatribe about this, but anyhow, so you see adrenaline here, which is responsible for the fight or flight syndrome. And there's more detail given on that in chapter 7. The next one is noradrenaline, and then you have dopamine over here. And then, of course, you guys probably recognize this compound here, but this compound is methyl our methamphetamine. So this is methamphetamine, okay? And there was a whole mini series called Breaking Bad, which was, the story of some guys making methamphetamine, selling it as crystal meth. And anyhow, I don't know if you guys have heard of ephedrine and pseudoephedrine and how that can be used to make methamphetamine. But anyhow, I won't get into the whole, chemistry of that. But anyhow, something kind of interesting there. So let's move on from there and talk about introduction to amines. So if we think about, trigonal pyramidal nitrogen of an amine carries a partial negative charge on its lone pair. Well, I don't need to tell you that if we draw, Mustafa, I'll answer that later. Okay, so if we look at ammonia, right, you guys all know that its molecular geometry is trigonal pyramidal, has a lone pair, right? The bond angle here is less than 109.5 degrees, right? That's from your old general chemistry days. Well, it says here that the trigonal pyramidal nitrogen of the amine carries a partial negative charge, right? So it's delta minus up here. And so it can function as a base or a nucleophile depending on the situation. And so if you put an amine in the presence of a strong acid like hydrochloric acid, it's going to protonate it to make an alkyl ammonium ion. And so this would be some kind of trialkyl ammonium chloride is what you would call that. And then here they're taking this tertiary amine and treating it with methyl chloride, which is a really good electrophile. And so we get a nucleophilic attack, we get a loss of leaving group. And so you just see an SN2 happening with an amine. So what's the bottom line for us as organic chemists is that an amine can function as a base or as a nucleophile. And you can imagine that in the chapter on amines, we're going to see both of them, okay? And so if this is a reaction you've been afraid of, something like this, okay? This is something that you would have seen many, many times in Gen Chem 1. So you would have seen this in Gen Chem 1 and 2, okay? So I want you to leave organic chemistry making sure that you're not afraid of these kind of acid-base reactions whatsoever, okay? Now, in terms of amines and discussing them as a group, before we can really get into, talking about synthesis and different reactions, we should know how to name an amine. And amines are widely used as reagents. And so all organic chemists have to know how to name them. So first one, it says, the IUPAC nomenclature gives you two different ways to name a primary amine. So far, all we're going to talk about are primary amines. Okay, so there's two ways you can do it. If the nitrogen is attached to an alkyl group that you can recognize, I mean, what are the alkyl groups you know? There's really 8 of them: methyl, ethyl, propyl, isopropyl, and then the 4 butyls: butyl, terbutyl, isobutyl, and secbutyl. If it's one of those alkyl groups, you can just use that. I guess I neglected to include all the cycloalkyl groups like cyclopropyl, cyclobutyl, cyclopentyl, cyclohexyl. You know those already. So if you can recognize the alkyl group, you can just name it and then call it an amine. So ethylamine, isopropylamine, cyclohexylamine, right? We could come up with other ones. Like, let's say you had this, right? You'd call that terbutylamine. Let's say you had something like this. You'd call that isobutylamine. Let's say you had 1, 2, 3 carbons, and then, right, you'd call that propylamine, so on, methylamine, et cetera, et cetera. So if you can identify the alkyl group, just feel free to use this nomenclature. There's no problem. However, what if your nitrogen is attached to some kind of group, right? We don't have a simple name for it. Well, in that case, you use the same nomenclature rules that you do for alcohols, but instead of the suffix "all" at the end, you literally use amine, okay? So let's say you had something like this, okay? So you could call this propylamine, but you could also call this you could call this 1,1-propane amine. Okay, that would also be like 1-propanol, 1-propane amine. And if you had this compound, right, we saw in the previous slide, you could call this isopropylamine, or you could call it 2-propane amine. Okay, either one is totally fine. And when do we use this rule the most? We usually use it when we have some kind of group that we can't just give a simple name to. So if you look at this compound here, obviously it's a primary amine, but this group is just way too big to give some common name. So we see that the longest chain that contains the functional group has 7 carbons. So it's some kind of not heptanol, it's a heptane amine. Okay, the amino group is at carbon number 2. So then we just label the rest: 4,6-dimethyl 2-heptaneamine, and you see that somebody identified this stereocenter as R and this stereocenter as R as well. So 2R, 4R, 4,6-dimethyl 2-heptaneamine. So that's how you name primary alcohol. Primary amine. So again, if you recognize the alkyl group, just give it the alkyl group name. Say sec-butylamine, good enough. Cyclopentylamine, great. Okay, but if it's some kind of group that's too long, then you name it like an alcohol. So just think of the alcohol, right? Heptanol, so it's heptaneamine. Propanol, so it's propaneamine, right? Ethanol, so it's ethaneamine. People usually don't do that. If they can identify the common name, they just usually use that, but both are acceptable. So where it gets more complicated are what about secondary and tertiary amines? Secondary and tertiary amines, okay? This gets much more interesting. But before we get to that, if you have an amino group or a primary amine as a substituent somewhere in a molecule, we just call it an amino group, okay? So if you have an NH2 group, okay, we can call it an amino group. And if you're saying, well, I thought you just said we would call it something amine. Well, remember, there's an order of precedence of functional groups. It's not covered in gross and gory detail in our text or in this class. But remember that if you have a functional group that contains an oxygen, like a carboxylic acid, aldehyde, ketone, alcohol, those are going to take precedence over an amine. And so here, you would call this an alcohol, and you would call this a carboxylic acid. So when your NH2 group is a substituent, okay, we just call it an amino group. And I'm sure you've seen that enough already to have picked up on that in the class. I'm sure you didn't need my help with that one. So an amino group. All right. Now, what I was trying to, another thing. So sorry, I'm trying to get to this point here, but I keep forgetting that also way back in chapter 17, when we discussed aromatic compounds, I told you had to remember the name of aniline. Okay. So aniline. So you've got to know how to name aniline derivatives as well, like metachloroaniline that's seen here, 5-ethyl-2-fluoroaniline, et cetera, et cetera. Okay, so just remember what aniline is. Okay, it could show up. Now, what I've been trying to get at is naming a secondary or tertiary amine. Now, it gives you multiple methods. Okay, but we want to make this as simple as possible. Okay, this is Chemistry 3111. We're still just kind of learning the subject. So here's what you do. If you can name the alkyl groups, right? You guys all know what an ethyl is. You know what a methyl is. You know what a propyl is. In that case, just list the groups in alphabetical order and then follow them up with amine. So we have ethyl, methyl, propyl, right? EMP, and then amine. That totally works. If you have two groups that are identical, like this one, you can use the prefix di. You don't call it ethylethylamine. You would call it diethylamine. And trimethylamine is this compound here. And before I started recording this video this afternoon, my students and I were talking about something called the fish odor syndrome. And what fish odor syndrome is, it's the inability to metabolize trimethylamine, which smells like rotten fish. It's the inability to transform it into an N-oxide, which is this compound here, which is odorless. But anyhow, I won't waste too much of our video time on that. Anyhow, now what if you have something that's much more complicated, right? Everybody recognizes a methyl. Everybody recognizes an ethyl. But what if you have this giant group over here that you don't recognize, okay? Well, in that case, follow the rule here. It says find the carbon parent chain, so that's the longest chain with the nitrogen attached to it, and then use the suffix amine. So here we have some kind of hexane amine. You see the nitrogen is on the third carbon, so it's some kind of hexane amine. Then what you do is you identify all the substituents. You have a 2,2-dichloro, you have an N-methyl and an N-ethyl. Remember, we use the prefix N to say that the methyl is attached to the nitrogen or the ethyl is attached to the nitrogen. Then remember, you ignore the di prefix and you ignore this N prefix. And so you would put the groups in alphabetical order. C for chloro, E for ethyl, M for methyl. So the stereochemistry here is S, so it's S, 2,2-dichloro, N-ethyl, N-methyl, 3-hexane amine. All right, give me a thumbs up if you're with me on the idea. At least the idea. You're going to have to try it for yourself. You know, nomenclature is one of those things that really has to be tried to be mastered. It cannot be mastered by simply watching it. So with that in mind, let's see if we can name a couple of amines. We'll call the first one Gary, and then we'll just move on. No, I'm kidding. Yeah. So let's see if we can name this one. We could use both methods here, because you guys recognize a cyclopentyl group and a methyl group. So what one's going to come first? Well, cyclopentyl is going to come before methyl. So we could call this compound, come on, pen, cyclopentyl dimethyl amine, right? That's one way to do it. Or we would look at the longest chain, which is the 5-membered ring. And if we had just this compound here, right? Think about it. If you had this compound, you'd call this cyclopentanol. So this must be cyclopentanamine. And then you have an N-dimethyl, right? Because you have a methyl on 2 methyls on the nitrogen. So if I just circle this, I'll put it in blue, and we'll just get rid of all of this. So how would I name that? I would call this N-dimethyl cyclopentanamine. All right. Okay. Does anybody have a name for the next one? Could anybody come up with a name for the next one? It's not a trick question. It's just there's 3 alkyl groups, and I know you recognize all of them. They're all identical. Yeah, thanks, Erica. Perfect. Yep. So like Erica says, the common name for this compound would just be triethylamine. Triethylamine. Triethylamine is actually so widely used that it actually has an acronym, which is TEA. You're like, can I have a cup of tea? No, thank you. That's triethylamine. That would be poison. Okay. But you could actually use the systematic way of naming this. I can't imagine why you would do it. Okay. But if you had this alcohol, right, that would be ethanol. So that means this would be ethanamine, right? Ethanamine. So technically you could call that NN-diethylethanamine. So NN-diethylethanamine. You'll have to check to see if they put that in the solutions manual. But if somebody asked me in the lab, like, hey, pass me the NN-diethylethanamine, I'd be like, what's wrong with you? Are you okay? You know, so nobody would call it that. Okay, and the last one is some kind of cyclohexanamine. So if we know it's a cyclohexanamine, and then we have this, so we have 1, 2, 3. So there's no common name that we could give to this because this group is just way too big. So it's some kind of cyclohexanamine, and we have a 3 isopropyl. So we'll say 3 isopropyl cyclohexanamine, like that. And so now we just need to figure out the stereochemistry at carbons 1 and 3, right? This is a stereocenter, this is a stereocenter. Well, carbon 1, so we go from, let me just take a look here quickly. So we have 1, 2, 3, so it's going this way. So it's S, so it's a 1S compound. And this one we go from 1 to 2 to 3, which is like that. So it's like this. So, nope, sorry, I'm wrong. It's a 1S. Am I doing it wrong? So, yeah, so it goes from 1 to 2 to 3. I knew I did something wrong. There we go. So it's an R. Okay, so it's a 1. What did I say? A 1S? Yeah, so it's a 1S, 3R compound. 1S. Not 2R, 3R, Mr. Dion. There we go. All right, so 1S, 3R, 3 isopropyl cyclohexanamine. There you go, my friends. Now you know how to name an amine. So let's see if we can draw some amines, and I'm sure you guys can do these faster than I can. The first one is tricyclobutylamine. So what do we need? We need a nitrogen, and then we need 3 things attached to it, and they're all cyclobutyl groups. There's 1, there's 2, and there's 3. So tricyclobutylamine. The next one is what? 2,4-diethylaniline. I'm sure you can all draw aniline faster than me. So aniline is just aminobenzene. You could call it that. I'm sure Wikipedia calls it that. So you need an ethyl group at carbon 2 and an ethyl group at carbon 4. And the last one, oh shoot, is 1R2S 2-methyl cyclohexyl 2-methyl cyclohexanamine. So let's try this. So what I always do is I will draw the compound like this, so 2-methyl cyclohexanamine. So let's put this here, and then we'll put our 2-methyl group out here, and then we'll see if our stereochemistry is correct or not. So on the first one, we go from 1 to 2 to 3, so that's going R. So when we reverse it, it's S. Am I right here? Okay, so we'll shade that in. So let's try it again. So we go from 1 to 2 to 3. So that's 1R, and then 2S. So we go from 1 to 2. No, hold on. 1 to 2 to 3. So that's 1 is R, and then 2 is, we go from 1 to 2 to 3. So that's going this way. So that's S. Is this right the way I put it? Something doesn't seem right about the way I've done this.
Would the lined one be shaded in since it's going to be going towards the
Yeah, I think I need more coffee or something because I'm looking at this and going, that doesn't look right to me. There's something squirrely about this. Let's try it again. So let's try this again. So if we have carbon number 1 is going to be an R. So we go from 1 to 2 to 3. So that's going in this direction, right? Does that seem reasonable to you? So that's an R. So that means it's an S, the way I've got it, right? So that means I have to reverse that one. So let's shade that in. Maybe I just need to talk through it more. I don't know. And then for the methyl group, okay, I've got the proton coming out. So I'm going to go from 1 to 2 to 3. So that's going like this, which is S. And so that means it's actually R. So that means I need to shade that in. Does that seem right to you guys? Yeah, I guess it does.
Yes.
Yeah, there we go. All right. There we go. Is that what the solutions manual says? Did anybody look? I don't know. Anyhow, hopefully that's right. It looks reasonable to me now. The first time I did it, I was like, that can't be right. Anyhow, there we go. Thank you. Whoever, was that you, Erica?
Yes.
Thanks, Erica. I appreciate it. All right. You guys are great. Okay, let's keep moving. So we got that one. Properties of amines. What did we cover? Stinky? No, I guess that's kind of important. So typical amines are sp3 hybridized. You know what's funny is that something that you might be wondering is, well, what if I had 3 different groups attached to a nitrogen, something like this? Would that be chiral, right? And if you remember back in chapter 5, that never came up, a chiral nitrogen. And there's a good reason for that, and that we're going to take a look at in just a second. So I'm going to put here a chiral, okay? So first of all, sp3 hybridization, bond angles. It's all you need to know for this class is less than 109.5 degrees is good enough for me. And that's just because the lone pair kind of pushes the alkyl groups down a little bit. What else? Carbon-nitrogen bond lengths are going to be slightly shorter than carbon-carbon bonds. Why? Because nitrogen is a smaller atom, but longer than carbon-oxygen bonds. Why? Because nitrogen is a bigger atom than oxygen. It says here, under what circumstances would a nitrogen be sp2 hybridized? I'll tell you the one you should remember. I'll underline this, is when it's part of an amide. Okay? So if you have something like this, right? This is N,N-dimethylformamide, or DMF. You look at this and you say, well, it's got 3 bonds and 1 lone pair. It's sp3. No, it is not. Remember, this lone pair participates in resonance, and the only way it can is if it's in a p orbital, right? So you could take your time here and draw the resonance form, which looks like this, looks like that, and then we have our nitrogen, right? So that lone pair, or that nitrogen, is sp2 hybridized, okay? So just keep that in mind, okay? That's something very important, and it's actually going to show up in the chapter on proteins and peptides and all that good stuff. So what else? It says here nitrogen atoms with 3 different alkyl groups are chiral, as they possess 4 different groups, but okay, what I wrote in the last slide is that they're achiral. Why? Because they're not optically active. Now, why would that be? So the rationale is this. It's actually because the trigonal pyramid inverts very rapidly. So it keeps going back and forth between the two. So technically, I guess it is chiral, but it doesn't rotate plane polarized light. So I think about it as being achiral, and that's just because it inverts very rapidly. Have you guys ever played the game Trouble before? Got the pop-o-matic bubble on it. You know, you have the die in here, right, or the number on it or something, right? And you press it down and it goes like pop, 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 right, back and forth. That's kind of the way you can think about an amine. It's just tut, 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 tut. The barrier to inversion is very shallow, right? It doesn't take a lot of energy to go in between the two like that. Now, other properties of amines, well, you know, what do I tell you guys in General Chemistry 1 or at the beginning of Organic Chemistry 1? What's something that never goes away in this class? It's what? Intermolecular forces, okay? London forces, dipole, hydrogen bonding. And so since a primary and a secondary amine are capable of hydrogen bonding, well, of course, it's got to come up in this chapter. So if you have an alkane like propane and you compare it to ethylamine or ethanol, what do you notice is that as you go from no hydrogen bonding to hydrogen bonding, right? This one only has London forces. This one has hydrogen bonding, right? As does the alcohol. But we know that the hydrogen bonding with an alcohol is a lot stronger than with an amine. Why is that? It's because amines are not, or nitrogen isn't as electronegative as oxygen, right? Oxygen has an electronegativity of 3.5, whereas nitrogen has an electronegativity of around 3.0. So the hydrogen bond just isn't as strong. So first of all, you have to know that trend. And then you also have to know this trend down here, that as we go from a primary to a secondary to a tertiary amine, what do you notice is that the boiling point just drops significantly for a tertiary amine. Why? Because it has no hydrogen bonding, whereas a primary and a secondary both possess hydrogen bonding. Give me a thumbs up if you're with me on these rationales, or does anybody have a question about those? So you have to know that amines can hydrogen bond. It's not as strong as an alcohol. And then I know that a few of you are really, you know, interested in biology and biochemistry and that kind of thing. And so you might have been in a lab where you had some unpleasant odors, maybe. You recognize this one here, cadaverine. So the odor of a cadaver, rotting flesh, is this 1,5-pentane diamine. And you've heard the word putrid before, so putrescine. So a lot of amines smell like rotting fish. And I brought up the fish odor syndrome earlier on, which comes from trimethylamine. But again, these amines smell terrible. It's not just trimethylamine. Triethylamine smells bad. Diisopropyl ethylamine, they all have a fishy odor to them. So working with amines, and just to give you some context, you know, when you have rotting fish, you've probably heard of people putting lemon juice on fish before. Why do people do that? Because in historical times, you know, if they had amines coming off of rotting fish, when they treated it with lemon juice has citric acid in it. It would protonate it to make the ammonium ion, which is odorless, right? This has an odor, but the salt is odorless. So that's where the idea of putting lemon juice on fish comes from. At least that's what I've been taught. It's historical. Yeah, there you go, Raul. If you have stinky fish, just put lemon juice on it. Everything will go away, okay? Now, in terms of your acid-base chemistry, pKa's, right? Is that something that never goes away? Oh, you bet your Bobby socks, right? So amines, we always think of amines as being bases, okay? As an organic chemist, you always want to think of an amine as being a natural base, okay? Now, they're stronger bases than things like alcohols and ethers, but it says that they can be protonated by relatively weak acids. So this is triethylamine, right? Triethylamine, I told you, has this SATSI acronym, which is triethylamine, TEA. Here we have acetic acid, which you guys know very, very well. Okay. If you look at the equilibrium between triethylamine and acetic acid, well, triethylamine, remember, an amine is a base. Acetic acid is an, you guessed it, acid. So the acid donates a proton to the amine. And then we end up with this. This is called a triethyl ammonium ion. And then this is acetate. Well, we have our base and our acid labeled. This would be our conjugate acid. and this would be our conjugate base. The equilibrium is going to lie to the side of the weaker acid. And you can see here that the pKa of the triethyl ammonium ion is about 11, whereas acetic acid is about 5. So the equilibrium is going to lie to this side. So that's why when you put lemon juice, which isn't a strong acid, with the stinky amine, it's going to protonate it, and you end up with something that is odorless. And it says here, it's useful to have a general idea of the pKa's of protonated amines. So we see this protonated triethyl ammonium ion is around 11-ish. Well, check this out. It says here, if you look at any of these ammonium ions, what do you notice? Let me just look at the numbers. You get 10.6, 10.6, 10.7, 10.8, 9.8, 11. So what would you say? The range is what? Around 9 to 11? If you have some kind of, right? If you have some kind of protonated amine, okay? The pK is going to be somewhere in the neighborhood of 9 to 11. Come on, that's close enough. And besides alkylamines, you have to have an idea of the pK of arylamines. Now, arylamines are going to have a lower pKa. So for an arylamine, so if we have a phenyl attached to our nitrogen, okay, it's going to have a lower pKa. So we'll put pKa is around 5-ish. Now, why would it have a lower pKa? It means it's more acidic, right? It's more willing to give up the proton. Now, why would that be? It means it's less basic. So why is this less basic? So if we compare, and this is something that we actually looked at in Organic Chemistry 1, but let's say you compare methylamine, okay, versus aniline. Which one of those is a stronger base? The answer is methylamine. So this is a stronger base. So if this is a weaker base, that means that its ammonium ion is going to be a stronger acid, right? Now, why would the aniline be a weaker base? It's because the lone pair is delocalized, right? It's not as readily available, whereas this lone pair is localized, okay? Now, that's something that I've gone over many times in the class, so I'm not going to harp on it for the next 5 minutes, but make sure you understand the difference between localized and delocalized electron pairs. And then this is something that we would have covered in chapter 17. So in the chapter on aromatic compounds and aromaticity, I explained why pyrrole is much less basic than pyridine. It's because the lone pair here is involved in aromaticity, and this lone pair has nothing to do with aromaticity. So if you protonate pyrrole, it goes from being aromatic to non-aromatic. So of course it wants to lose that proton, whereas pyridine is aromatic in the pyridinium ion. This thing here is also aromatic. Why? Because the lone pair has nothing to do with aromaticity. It's in an sp2 hybrid orbital. All right. So other properties of amines. It says here, if you have an amine with more than 5 carbons, it's only going to be slightly soluble in water. If you have an amine with less than 5 carbons, generally speaking, it's going to be soluble in water. But you can enhance the solubility of an amine by protonating it. Like, let's say you have something like this. Okay, you have 1, 2, 3, 4, 5, 6. You have hexylamine or hexanamine. Right? This is only going to be slightly soluble, but if you treat this with HCl, then you end up with what? You end up with NH3 plus, Cl minus. This is a salt. This is going to be very soluble in water, okay? So slightly soluble in H2O, very soluble in H2O. So what does this mean? It means you can extract an amine from organic impurities by using aqueous acid. You just treat it with acid, you get the salt, and then it's going to go into the aqueous phase. And it turns out that many pharmaceuticals contain one or more amine functional groups and are marketed as salts. You see Gleevec here is a cancer medication, right? It's got a salt in it. What else? This compound that's used to treat hypertension is a salt. And then Viagra. You see that Viagra is also a salt. Here's the cations. Get this big anion over here. But there you go. So there are many drugs that are marketed as salts. All right. Now, the pKa of most amine conjugate acids, so we said if you have something like 3 alkyl groups, okay, or even 1 or 2, whatever, it doesn't matter, right? That has a pKa between, what did I say, 9 and 11? Here it says 10 and 11, close enough. The arylamines are less basic. I already went over this with you. Why? Because the lone pair is delocalized. So it's, delocalized inside the ring, so it's not as available for protonation. So arylamines are weaker bases than alkylamines. And I went over the pKa's for protonated arylamines. They're in the neighborhood of 5, okay? But you see that you can mitigate it or moderate it by changing up the group that you put on the ring. So if you have an electron donating group like a methoxy group, that's going to make it more basic. So therefore, the conjugate acid is going to be a weaker acid. But if you have an electron withdrawing group like a nitrile, that's going to make it a weaker base. So you end up with a stronger acid in the end. So make sure you're aware of that effect. And then, of course, make sure you understand an amide, that the nitrogen, the lone pair in a nitrogen of an amide is not basic whatsoever, not even a little bit. Why? Because it's delocalized into the carbonyl, because it is resonance stabilized. Now, at physiological pH, it turns out that most amines exist primarily as an ammonium ion. So if you have the amine, okay, the amine, and then you have an acid, okay, this is your alkyl ammonium ion. Well, if we look at the Henderson-Hasselbalch equation, it says here, recall the Henderson-Hasselbalch equation, the HH equation, can be used to calculate the ratio of amine to ammonium at a given pH. So let's say, did I do the calculation? Oh, I didn't here. So let's say you have physiological pH, and I don't have a lot of room, but let's say you have physiological pH, which is 7.3, and the pKa of an alkylamine is 11. Well, then you're going to have the log of the conjugate base is going to have to be lower than the log of the acid, right? You're going to have a bigger number for the acid in order to get a negative number. Are you with me on that? Right? You get a number smaller than 1 and you get a negative number with your log. I should have put log there, my mistake. But anyhow, log of 1/2. It's just an example, okay? So that's why the acid predominates at physiological pH, or the ammonium ion. Okay, so now what we're going to do is we're going to rank these amines in order of increasing boiling point. So we've got a tertiary amine, we've got a primary amine, and we've got a secondary amine. So could anybody tell me which one of these is going to have the highest BP? Anybody? Which one would have the highest boiling point? Would it be the primary, secondary, or tertiary? If you have to go back in your notes. Which one can do the most hydrogen bonding? Would it be the tertiary, secondary, or primary? No. The one that can do the most hydrogen bonding is the one that has the most bonds to hydrogen, right? So here we have RNH2, right? So we have 2 possibilities for hydrogen bonding. Here we only have 1, and here we have none. Okay? So the highest boiling point is going to be the primary, exactly. So primary is going to have the highest boiling point, the tertiary will be lowest, and the secondary is somewhere in the middle. Now, the rule that we said for solubility was if you have less than 5 carbons, so if you have less than 5 carbons per amino group, then your compound is going to be H2O soluble. So if we look at the first compound, you see that we have a total of 6, 7, 8 carbons per amino group. So this is not H2O soluble. If we look at the second compound, it's got 3 carbons per H2O or per amino group. So this is, we'll just say yes, will be water soluble. What about the last one? Would the last one be water soluble? Anybody? Remember, we want to have 5 carbons or less per amino group. So would the last carbon be water soluble? Or the last compound be water soluble? Anybody have an idea about that one? So this one, if you count the total number of carbons, you have 6 carbons per 2 amino groups. So therefore, it's going to be 3 carbons per 1. Therefore, yes, this will be water soluble, like that. Great. Now, for the next one, it says identify for each of the following pairs of compounds which one is going to be a stronger base. So if we put in all the lone pairs, so we're missing a lone pair here, 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 and here.